In this section, we will discuss managing default permissions and file access. Specifically, we will look at the special permissions and how they alter the behavior of default permissions, as well as the command umask, which influences permissions of new files. Let's begin by looking at the special permissions. There are three special permissions: a set UID, a set GID, and a sticky bit. They have a slightly different effect depending on whether they are applied to files, specifically executable files, or directories. Let's begin with the effects on files. The set UID and the set GID bits on executable files are designed to alter the ownership of the process when a file is executed. For example, the password command modifies a user's password. Those passwords are stored in the etc shadow file. If we look at the permissions of that file, it is not accessible by anyone, so you must be root in order to modify this file. Yet if I run the password command, I'm able to update my own password. Normally when I execute a command, it would run as me, in this case student, and I would not have that privilege. So if we look at the permissions for the executable itself, which is in the user bin directory, we see that the permissions are executable by everybody, but there's this additional S that shows up in place of the X for the user field. This indicates that the set UID bit is set for this particular file. The meaning of this bit is that when this file is run as a command, the process that runs will run as the owner of the file, in this case root. Since the process is running as root, it would have the ability to update any file on the system, including the etc shadow file. You should be aware that this can be a security risk depending on what the process itself does. In this case, if I run the password command and I even give my own username, I get told that only root can specify a username. So it's built into the process itself to make sure that just because it runs as root, not just any user can change anybody else's password. The set UID bit is designed to alter the process ownership. The set GID bit does a similar change to the process group affiliation. Again, normally when I run the process, it would get the group affiliation from the user that issues the command. But if the set GID bit is set, then it would get the group affiliation of the file itself. To set these permissions, we use the change mode command. We can do it symbolically or numerically. Let's take a file that I have locally. For example, my read-only file. Let's make a copy of that and just call it random file. Let's imagine that this is a binary or a script, and we want to now make it executable. Perhaps I use the change mode command and I give all privilege to my owner, I give read and execute to my group, and I give read and execute to others for this particular file. If this script or binary was run, it would run with the credentials of whoever was actually issuing the command. If I want it to run as the owner of the file, in this case student, I can use the change mode command. Symbolically, I can say U plus S on this file, and I've added the S bit there, and now it will run as student regardless of who actually issues the command. G plus S would set the set GID bit. Numerically, we use a fourth preceding digit. Set UID has a value of 4, set GID has a value of 2, and sticky has a value of 1. So for example, to set these same permissions, I can say 4755. The initial digit, the 4, is my special permissions. I have the set UID bit only. Then I still have my owner permissions, my group permissions, and my other permissions. Looking at the file permissions, they should not have changed. If I want both the set UID and the set GID bit, I can say I want 4 plus 2 or 6 for my special permissions, and then specify my user group and other permissions. The set GID bit shows up in the group permissions, and again as an S in place of the X field. The third special permission is the sticky bit. It has no effect on an executable file, but it does have an effect on a directory. Recall that we have the ability, if we have write access, to delete any file within our directory. So if I look at the current permissions of my current directory, I'm the owner and I have write privilege. There's this file that is owned by root file that I do not have write privilege to because other is read only. Yet because it's in my directory that I have write privilege to, I'm able to delete this file. On the other hand, if we take a look at the temp directory, a shared space, everyone has read, write, and execute to this directory, but there's this T within the other field. This represents the sticky bit and is set symbolically with an O plus T or removed with an O minus T. This bit on a directory means that I must own a file in order to delete it. So if I look inside of the /temp directory, there is a file that I own, in this case myls3. I should be able to remove this file without a problem. I have write privilege in /temp, so I can create files and I can delete files, and I deleted a file that I owned. However, because the sticky bit is set, if I try to delete someone else's file, for example, I try to remove the yum.log file that's owned by root, even if I say yes, I want to remove this write protected file, I end up with an operation not permitted because of the special permission, the sticky bit, on the directory, forcing me to not be able to delete anyone else's files. It's very useful for shared space such as /tmp. The set GID bit also has an effect on directories. It has an effect, however, on creating new files. Let's go back and look at home shared. This is a directory that the wheel group has write access to. As the user student, I am a member of the group wheel, and I was able to create files in this directory. Remember that they're owned by myself, student, and my primary group, which is also student. In order to collaborate, I might need to go back and change the group affiliation with these using the change zone command. It would be nice if I could have that change be automatic for a shared directory where collaboration is going to occur. That's what the set GID bit will do on a directory. It will indicate that new files in that directory inherit the group affiliation of the directory itself instead of the primary group of the user that creates that file. Home shared is owned by root, so let me switch to the root account and let me set chmod g+s on home shared. If I look at the permissions, I now see the S bit there in the group permissions. I can return to the student account now, and I can touch in home shared a new file. If I look at the permissions of that file, I see that I own it, student, but that it got the group wheel. Instead of my primary group of student, it inherited the group affiliation of the directory itself. It's also important to note that the previous files that were there did not change. This bit only has an effect on newly created files. The set UID bit has no effect on a directory. So we have three special permissions, the set UID, the set GID, and the sticky bit. On executables, the set UID and set GID bit have an effect on the ownership and group affiliation as an executable is run as a process. On directories, the set GID bit helps with creating new files in that directory for collaboration, which will automatically get the group affiliation of the directory itself. And the sticky bit helps with shared space in forcing a user to only be able to remove files in that directory that they own and not be able to remove other users' files. The other aspect of controlling default permissions and file access is associated with a command called umask. If I create a new file and I look at its permissions, the permissions that are granted are based off of the maximum permissions that would be allowed. For example, for a file, this would be read-write, read-write, and read-write. Ordinary files are not given execute permission automatically. If I create a new directory and I look at their permissions, the maximum permissions that would be granted are read, write, execute for all of the fields, the user, the group, and the other. Yet that's not what I'm seeing with these two examples. Umask by itself will show me what my current umask is. This is a value that's used to mask or take away from the default permissions when new files and directories are created. Zeros represent no change. Other values represent the permission bits for that field that should be masked or taken away. In this case, no change to special permissions, no change to the owner permissions, no change to the group permissions, but remove the write privilege from other permissions. And this is reflected through the permissions that were made on my new file, where other does not have write access, and my new directory, where other does not have write access. If I set my umask to 0, I can set it by simply typing umask space and the value that I want it to be. It assumes leading zeros, and then I can view it again. With a umask of 0, I'm doing no masking at all. If I create a file in a directory, they will have the system defaults for new files and new directories. So I'll touch new file 2 and look at its permissions, and I'll make a directory new dir2 and look at its permissions. And I see that read and write is allowed for everybody on both, and execute is also given to the directories. Ordinary files, again, do not get execute by default. A more common umask to use would be to mask out the other fields. So umask 007. Again, I could drop the leading zeros and simply put a 7 there. If I type umask, I see that my umask is now at 007. And if I touch new file 3, if I make a new directory, I see that there's no change to the defaults for the owner, read write for the file and read write execute for the directory. No change to the group permissions, but all permissions, read write and execute, have been removed from other. One final common example would be to set my umask to 027, which would take the group affiliation or group permission away from files, as well as all permissions away from other. Again, my umask is now 027. No change to the special permissions, no change to the owner permissions. Remove write access from the directory and remove all privilege from the others. The umask is set every time a shell is started. This means in order to change what our defaults are, we need to look at the system-wide login scripts and bashrc scripts. We could also override for an individual user in the .bashrc file. Let's begin by looking at the etc bashrc file. If I use less, it's easy to search, bash rc, do a slash for searching inside of less, and search for umask. It's inside of an if then else. Basically, if I'm a normal user with a UID above 199, greater than 199, I get a umask of 002. Otherwise, I get a umask of 022. If I switch to the root account and type umask, I see that root gets 022. If I switch to a user, like student, and I look at the umask, it gets 002. If I exit back to where I was last working and I change the umask, that is where I last set it at 027. So each time I log in, it would come from the login scripts. I could change it after the fact, or I could modify the scripts for a more permanent change. I do need to modify both scripts. For example, the etc profile and searching for umask has the same setting in it. So it could be set as I log in with etc profile, or it could be set as I start an additional shell with etc bash rc. Changing these permissions, I could choose a umask that I want for my system-wide default, perhaps 007, and save that change. And because I'm not root, I'm not able to make that change. I'll have to switch to root in order to do that change. Once I do, I would have to log out and log back in again. A final alternative would be to look in my home directory at a .bashrc file. At the very end, I could add a umask command. So for example, I could echo umask 027, and I could append that to my .bashrc file. And now when I log in again as student, and I look at the umask, this time I got 027. So the umask is used to control the permissions that are assigned for new files. It has no effect on existing files, only is looked at when creating new files. A user can change their umask from the command line with the umask command, or that command could be added to a script, either in the user's home directory in the .bashrc file, or system-wide if you're the root user in the etc profile and the etc bashrc files.